Stator voltage control of an induction motor drive. As we've seen, the speed and torque of an induction motor can be varied by one of the following means, that is techniques, in which the stator voltage control of an induction motor is the first one. From the previous topic, we got an equation number 18 that Td equals to 3 RVS square divided by S omega S of Rs plus RR by S whole square plus XS plus XR whole square. Now this equation indicates that the torque is proportional to the square of Vs, stator supply voltage, and a reduction in Vs will produce a reduction in speed. If the terminal voltage is reduced to BVS, then equation number 18 gives the developed torque Td as Td equals to 3 RR BVS whole square divided by S omega S of Rs plus RR by S whole square plus XS plus XR whole square, where B is less than or equal to 1. This figure shows the typical torque speed characteristics of various values of B. You can see for B equals to 1, this is the characteristics of a torque speed or torque slip. If the B is 0.75, then this is the characteristics. The point of intersection with the load line defines the stable operating point. Here it is for the B 0.75, and this is for B equals to 1. In any magnetic circuit, the induced voltage is proportional to flux and frequency. That VA equals to BVS, which is equals to Km, it's a constant, and frequency and flux. And the air gap flux can be expressed as phi equals to VA by Km omega, which equals to BVS by Km omega. That is equation number 31. So where Km is the constant, depends on the number of turns of the stator winding. As the stator voltage is reduced, the air gap flux and the torque also reduced. At lower voltage, the current will be peaking at a slip of SA equals to 1 by 3rd. The range of speed control depends on the slip. For maximum torque Sm, for low slip motors, the speed range is very narrow. This type of voltage control is not suitable for the constant torque load and is normally applied to applications requiring low starting torque and narrow range of speed at relatively low slip. The stator voltage can be varied by 3 phases. The first one, AC voltage controller, and second one, voltage fed variable DC link, and third one, PWM inverter. However, due to the limited speed range requirements, the AC voltage controllers are normally used to provide the voltage control. The AC voltage controllers are very simple. However, the harmonic contents are high and the input power factor of the controller is low. They are used mainly in low power applications such as fans, blowers, and centrifugal pumps, where the starting torque is low. They are also used for starting high power induction motors to limit the inrush current. This is regarding the stator voltage control of an induction motor. And second type of control is the rotor voltage control. In a wound rotor motor, an external 3-phase resistor may be connected to the slip rings as shown in this figure. The developed torque may be varied by varying the resistance Rx. If Rx is referred to the stator winding and added to RR in equation number 18, may be applied to determine the developed torque. The typical torque speed characteristics for variation in the rotor resistance are shown here. This method increases the starting torque while limiting the starting current. However, this is an inefficient method and there would be imbalance in the voltages and the currents. If the resistance in the rotor circuit are not equal, a wound rotor induction motor is designed to have a low rotor resistance so that the running efficiency is high and the full load slip is low. The increase in the rotor resistance does not affect the value of maximum torque but increases the slip at maximum torque. The wound rotor motor are widely used in the applications requiring frequent starting and braking with the large motor torques, like cranes and hoist. Because of the availability of the rotor winding for changing the rotor resistance, the wound rotor offers greater flexibility for control, but it increases the cost and needs maintenance due to slip rings and bushes. The wound rotor motor is less widely used as compared to the squirrel cage motor. The three-phase resistor may be replaced by three-phase diodes, rectifier, and a chopper here as shown in this figure, where GTO operates as the chopper switch. The inductor LD acts as the current source ID, and the chopper varies the effective resistance, which can be found from the equation that R equivalent equals to VB by IB, which equals to RB 1 minus K plus RM. And here R equivalent equals to R 1 minus K, where K is the duty cycle of the chopper. The speed can be controlled by varying the duty cycle. The portion of air gap power which is not converted into mechanical power is called slip power. The slip power is dissipated through the resistance R. The slip power in the rotor circuit may be returned to the supply by replacing the chopper and the resistance R with a three-phase full converter as shown in this figure. The converter is operated in inverse mode with a delay range of pi by 2 less than or equal to alpha less than or equal to pi, thereby returning energy to the source. The variation of the delay angle permits power flow and speed control. This type of drive is known as static KRAMERS drive. Again, by replacing the bridge rectifier by three-phase dual converters or cycle converters, as shown in this figure, the slip power flow is either direction is possible, and this arrangement is called as static SCHERBIUS drive. Static KRAMERS and SCHERBIUS drives are used in large power pump and blower applications where limited range of speed control is required. Since the motor is connected directly to the source, the power factor of this drive is generally high. This is regarding the rotor voltage control of an induction motor. If this video is useful, please like, share and subscribe.